Human language is a chaotic, continuously shifting stream of variable length, but a multi-layer perceptron operates on rigid mathematical boundaries. Machine learning models cannot process raw strings of characters. They operate exclusively on fixed numerical tensors. First, tokenization segments the continuous string into discrete blocks. Then feature mapping translates those tokens into dense matrices of numerical values. These embeddings represent semantic characteristics, but feed-forward AI models require completely static, fixed-size dimensional matrices to function. Human sentences do not conform to fixed structures. They contain unpredictable, highly variable word counts. To compute language at all, an architecture must utilize a sequence layer. This specific processing stage compresses any varying length of text into a unified, fixed mathematical representation, without destroying the underlying meaning of the words. The absolute simplest and cheapest mathematical mechanism to satisfy that static input requirement is a uniform aggregation layer. On screen, we see how this works. The equation simply takes 1 over n times the sum of the word embeddings. It computes a single fixed-size sentence vector by calculating the uniform mean of all the individual words. Look closely at the result. The mathematical output vector for John loves Mary and Mari loves John is completely identical. This operates under the bag of words paradigm. Because the positional order of the inputs is completely ignored, the aggregation destroys all syntactic meaning. To capture structural word order, early text models turned to windowing, a localized strategy that forms the foundation of convolutional neural networks. This visualization shows the windowing mechanism in action. Following the equation m plus n plus 1, the model captures a target token alongside a static number of past, or n, and future, or m, words. When the target word sits at the absolute boundary of a sequence, the system handles the lack of historical context by inserting zero padding matrices. Windowing successfully guarantees static input volumes and preserves local syntax, yet it creates a narrow receptive field. The network remains blind to long-range sequential dependencies. To solve for global context, engineers introduced the recurrent neural network. This mechanism processes data chronologically to carry information across an entire timeline. This node graph maps the core architectural shift of the RNN. It maintains an internal memory loop, passing a hidden state vector forward from a previous time step directly into the current processing block. Inside that block, the weight-scaled previous history is mathematically added directly to the scaled current input feature. A hyperbolic tangent activation function then clamps this combined sum strictly between -1 and +1, preventing the values from exploding as they compound. This sequential looping theoretically compresses a complete global history of the text into one single continuously evolving vector. In practice, it hits a wall. As sequences grow longer, distant historical signals degrade, because they are continuously overwritten into a single constrained vector size, a flaw exposed during backpropagation through time. A functional architecture requires unconstrained global context across long distances without the constraints of a degrading sequential loop. The solution is self-attention. It operates as a dynamic, database-style retrieval mechanism that evaluates all global contexts simultaneously. In this diagram, we see the foundation of the mechanism. The network projects a single raw word embedding into 3 distinct functional vector subspaces: the query, the key, and the value. The query vector acts as an active probe. It evaluates the alternative positions across the sequence. The key vector serves as a comparative index. It acts as an address, matching against incoming queries from other words. The value vector contains the actual semantic content payload of the word itself. Here is the scaled dot product attention equation that brings them together. The network computes raw alignment scores between words by calculating the mathematical scalar dot product of all queries and keys. The denominator introduces a scaling factor based on the dimension of the keys. This stabilizes training by preventing high-dimensional variance from crashing the upcoming gradients. The softmax function takes those arbitrary scalar scores and normalizes them into a strict probability distribution ranging from exactly 0 to 1. Finally, the system uses those normalized percentages as blending coefficients, computing a context-customized weighted sum of the value matrices. By processing alignment scores directly, self-attention allows any word to extract exact context from any other word in a single computational step, entirely bypassing the sequential degradation of the RNN. However, self-attention contains a massive structural vulnerability. Because it calculates matrix dot products simultaneously in parallel, the math is inherently permutation invariant. Without chronological order, the attention engine cannot differentiate John kills Mary from Mary kills John. It reverts to a highly advanced bag-of-words paradigm. This equation visualizes the mathematical fix, positional encoding. The network generates unique sine and cosine wave vectors mapped to a word's absolute index position. This structural vector is added element-wise directly to the semantic word embedding before entering the attention block. Positional encoding allows the architecture to achieve the massive efficiency of parallel matrix computation while retaining the exact syntactic awareness of a recurrent loop. With the context mathematically secured, the finalized sequence representations are routed to the output layer for task execution. In sequence classification, the final layer condenses the entire sequence matrix into one single vector to output a singular GLOBA prediction label. In sequence labeling, the network skips aggregation, routing each distinct position state into its own classification head. Schemas like the BIA format use structural prefixes to group tokens into multi-word spans. This token-by-token dimensionality creates an exponential search space, rendering brute force prediction mathematically impossible. The transition from simple, uniform averaging to positional self-attention provides the unconstrained routing required to model language at scale. These architectures map the variability of human text into precise geometric spaces, ensuring that context remains intact across the entire sequence.